Hello, this is Mr. Gilmore with the 8.2 Part 2 Pythagorean Triples lesson. This is a continuation right from the Pythagorean theorem that we proved in Part 1. As we're going to find out, there's some actually special sets of numbers that work with the equation a squared plus b squared equals c squared. Let's dive in. So we have the definition of what a Pythagorean triple is. A Pythagorean triple is a set of three whole numbers, a, b, and c, such that they satisfy the equation a squared plus b squared equals c squared. Now recall what your whole numbers are. These are values that are not decimals, not fractions, not negative. We're talking about our 0 and our positive integers, right? 0 through infinity. So we're looking at a special set of three numbers that when plugged into this equation, it satisfies it. It makes it true. And if it does make it true, well, then we have what's called a Pythagorean triple. Now, an obvious property of a Pythagorean triple is that then those three numbers, those three whole numbers, would be the side measures of a right triangle. They would form a right triangle. Why? Well, because it satisfies that equation a squared plus b squared equals c squared, and we've proven this. This is the Pythagorean converse. So since it satisfies that equation, we then can conclude that the Pythagorean triple is a set of three whole numbers that form a right triangle as well. So let's check a few sets of triples and see, do they satisfy the equation a squared plus b squared equals c squared? And if they do, then we can call that set a Pythagorean triple. Let's check it for these two sets, the 3, 4, 5 and the 5, 12, 13. Let's go ahead, and what we do is we order these from least to greatest, which means this is in order A, B, C, and this is in order A, B, C, and we're going to test it for both of them. Let's start with our first 3, 4, 5. So we have 3 squared plus 4 squared. And the question is, does it equal 5 squared? Well, as we simplify, 9, 16, 25. 9 plus 16 is 25. So yes, that is a Pythagorean triple. It's a set of three whole numbers that satisfy the equation a squared plus b squared equals c squared. Let's do that for our second set of triples here. We have 5 squared plus 12 squared is equal to 13 squared. Is that true? So we then evaluate and simplify here. We have 25 then plus 144 is equal to 169. 25 and 144, guess what? They make 169. 169, very good. That is another Pythagorean triple. So then the question is, how many Pythagorean triples are there? There's a lot of them. Right? This is not even all of them on the screen. All of these were taken from a website, but as it was proven, actually the Greeks knew this, the Greeks proved this, that there is an infinite set of Pythagorean triples, and this is just a small portion of the first initial set of Pythagorean triples. As you can see, there's a lot of them in here. And you can see the very first two we just tested, 3, 4, 5, 5, 12, 13. But there's some in here like, like 120, 209, 241. That's a cool Pythagorean triple. Down here we got 23, 264, 265. That's a cool Pythagorean triple. Now, I'm not expecting you to know all of the Pythagorean triples. You'll see later on that I'm going to point out a few of the lower ones for you. A few of the lower ones that I'll pick out from the top here would be like 8, 15, 17 would be a good one, 7, 24, 25, 9, 40, 41. Those are all good ones to spot. Even the 20, 21, 29, those are all good small numbers to spot, saying, oh, wait, I recognize that as a Pythagorean triple. So a Pythagorean triple actually comes in two forms. Okay, it's either going to be a basic Pythagorean triple or a non-basic Pythagorean triple. What does it then mean for a Pythagorean triple to be called basic? So we call a Pythagorean triple basic if the greatest common factor of its three members is 1. Now remember what it means to be a factor. You take a number, break it down into what numbers divide into it, and if the only number that all three numbers share is 1, then it's called a greatest common factor of 1, and that makes the triple a basic triple. So let's go and take a look at our triple 3, 4, 5 again. Is that a basic triple? It is. The largest factor that all these three have in common, 3, 4, and 5, the reason why they would be considered basic is because the greatest common factor between all three of them is the number 1. In some areas of mathematics, we call the greatest common factor the GCF. So the GCF here is 1, which means we've got ourselves a basic triple there, 3, 4, 5. But let's take a look at our second triple here, 6, 8, 10. Is that a basic or non-basic? It's actually a non-basic, because if you take a look at the three terms, three values there, 6, 8, and 10, all have a common factor of 2. And that's not 1, right? It's greater than 1, which means the GCF being 2 makes this a not basic Pythagorean triple. And so you're going to encounter along the way that there will be some triples in the form of basics because they have a common factor greater than 1 that separates them from this basic Pythagorean triple. Now, let's talk about the non-basic triples, okay? To create any non-basic triple, it's very simple. Take any basic triple, or really not any, take any triple, basic or not, and multiply each member by a whole number 2 or greater. So down below, we actually see the example we used on the previous slide, that we have this basic triple, 3, 4, 5. When you multiply all the values in that triple by 2, it turns into 6, 8, 10, which means you form another triple. Now that triple you formed is obviously going to be non-basic, but you can form any non-basic triple by using a basic or not basic triple. Just multiply it by a common multiple. Now, why then would be a non-basic triple itself be a Pythagorean triple? So if we start off with a basic Pythagorean triple, or a non-basic Pythagorean triple, and you multiply it by a number, by some sort of factor, why would it itself still be a Pythagorean triple? Well, I think the answer is obvious here. Similarity. Similarity is the powerful tool we have here, because what is that factor we're multiplying the triple by? It's multiplying it by the scale factor. Okay, we'll find that all 3 sides of one triangle are in fact proportional, all 3 sides another. That's using side similarity, which then means we know we'll have similarity between the 2 triangles. So if the basic Pythagorean triple is in fact a right triangle, then any non-basic will also have to be a right triangle, which means it does fit into the sense of it's a Pythagorean triple, right? So it's just simply a scale of the equation Pythagorean theorem. Imagine this, that we took our equation, a squared plus b squared equals c squared, and you multiply it by some scale, k. Well, then everything turns into this equation, k times a squared plus k times b squared is equal to k times c squared. So it's still going to satisfy the equation regardless, thanks to similarity and the scale factor we find between the 2 polygons. So now, how do we use them? Why is it important that we study the Pythagorean triples? Well, it's because you're going to save yourself some time by recognizing Pythagorean triples. In fact, when you get into Algebra 2 and even pre-calculus, you're going to find that they use a lot of Pythagorean triple triangles, and it's going to save you a lot of headache, a lot of time trying to find any missing sides of a right triangle if you already know it's going to be that of a Pythagorean triple form. So some of the smaller ones you want to point out, or want to actually study, and you'll begin recognizing these over time as you begin to experience them more. So these 4 here would be some of the smaller ones, right? 3, 4, 5, 5, 12, 13, 7, 24, 25, 9, 40, 41. There are a couple other small ones we add there, but these 4 usually pop up a lot. You see them quite often, usually, again, in other areas of mathematics. Even I've seen some on the PSAT, SAT, as those come up in the terms of what are we looking for in the right triangle. Well, if you recognize it's a Pythagorean triple, you can save yourself a lot of time. So let me show an example of saving yourself some time using Pythagorean triple. So again, how do we use them? Well, whenever you see a triangle, right triangle specifically, when only 2 members are given of that triple, but you recognize it to be a triple, then you can fill in the 3rd member very quickly and without having to actually touch the Pythagorean theorem to figure out what that missing side is. Then you can figure out what the missing side of the triangle is if you recognize that it fits into the set of Pythagorean triples. So if you use these 4 examples below, take a look at the first triangle, 3, 4, blank. Well, we're missing the hypotenuse. Well, that fits right into the pattern 3, 4, 5. And then I can continue that for the second one. Take a look, it's a 5, blank, 13. Well, wait a minute, I know what that is, 5, 12, 13. The third one, 7, 24, 25. Our last one, 9, 40, 41. So begin to save yourself a lot of time by recognizing Pythagorean triples. So you're going to hop over and take a look at the Pythagorean triple worksheet, in which you'll use Pythagorean triples to find missing values. You're going to be using the Pythagorean theorem in a little bit of the section, but the majority of the homework is you're going to be using the Pythagorean triple idea to find missing side measures without even having to touch a calculator. So we've come to the end of our lesson. If you do have any questions on the worksheet, please do not hesitate to ask. With that, be good and do good.